So, very good morning to all. Welcome back. I hope most of the scholars joined the meeting.
Good morning, sir.
Now, let us start the today's discussion. If I'm talking about the content or syllabus for this subject, which is linear algebra, so which is almost completed. Most of the things we have completed in offline classes, and the rest we have covered in yesterday class. Now, what left? It is only two small definition: what is full matrix and what is sparse matrix, and there are what are there some of the applications. So what I'm planning today, first we will discuss about what is full and sparse matrix, their application, and then we'll discuss about the Jacobi method for finding the eigenvalues and eigenvectors. Also, we have discussed the same method in the offline classes, but we didn't solve sufficient example as I feel. Only one example we have done over there. So after this definition of matrices, full and sparse, we will proceed to take one example for Jacobi method for finding the eigenvalues and eigenvector. Obviously, that method is iterative method. So those who was present can revise the concept, and those who was absent can try to understand it. So now I'm going to share the screen. Before that, if there is anyone having any concern, then he or she can ask for it. If there's any concern from your side? Okay. So no concern. So let us proceed. I hope all of you are familiar with the term matrices that we have done in offline classes. Things related to the matrices like solution of system of equations, that how we can find the solution of an inconsistent system of equation, eigenvalues, eigenvectors, iterative methods, and many more things. So continuation in the same, we will discuss these two definitions first. So the first one is sparse matrix and the second one is a full matrix. So if I'm talking about application point of view, both of them is having wide range of applications. Because what happens when we are taking a problem in real life situation, in a real world problem, then it's not a kind of matrix that we are generally dealing. Like we are ideally dealing with a matrix whose order is like 2 by 2, 2 by 3, 3 by 3, at most 4 by 4 generally. But what happens when you are model of physical phenomena, problem arise in the industry in terms of a matrix, then the dimension of the matrix is not like 3 or 4 by 4. It's too large. Sometime it may be a matrix we are getting 100 by 100, 1000 by 1000, even more than that dimension. So in that case, as we know that we are having limited memory when we are running a program through any software, either it is MATLAB or Mathematica or something else or some other software that we are using. So what we need to do, we need to optimize the inputs so that the memory can also be optimized. So for that concern, we are having sparse and full matrix. Like what is a sparse matrix? A matrix is said to be sparse if it is having most of the element as zero. So if we are having a matrix whose most of the elements are zero, we call it as a sparse matrix. Now, many concerns rise in this definition that what we mean by most of the elements. So some of the author is saying if we are having 80 or more than 80% elements are zero, then we are saying sparse. Some of they are saying if 50% is zero, we can consider it. But as a majority of the author is saying, if a matrix is having 60 to 65% on the lower side, minimum 60 to 65% elements are zero, then we call it as a sparse matrix. Obviously, more than that is also considered, but the least or the lower side for this is 60 to 65%. So the matrix is called as a sparse matrix. So now we can correlate it with the relation, like suppose we are talking about the Facebook data. So on Facebook, we are having many number of individuals. So if I want to show them with the help of a matrix and want to give this matrix as an input to the Facebook database, then it's not quite obvious to prepare the matrix in the standard form. So what we can do over there, we can simply give those input which are non-zero. Means what? Suppose that I'm taking a simple example. There are 1,000 individuals. Just take a simple example. So if I draw the relationship between the 1,000 people to one another, we will get a 1,000 by 1,000 matrix. Thousands rows are there and 1,000 columns are there. Now the entry of the matrix can be means considered as, like, if an individual A is connected to individual B, then we can say that entry comes out as 1. If no relation, we will consider it as a 0. We will consider, or we can write it as 0 or something else, whatever we are assuming. So I'm taking, if two individuals are connecting on Facebook, we can put it as 1. Not connecting, we can put it at 0. So in this case, if I'm taking 1,000, so 1,000 is a small database. If we are talking about Facebook, it may be crores or like million or trillions individuals, those who are using Facebook. So if I'm making that square matrix, so in that cases, most of the elements are 0. So this is one of the example of the sparse matrix. So in place of putting the whole matrix into database, we can only put the non-zero entries in the database, and this can be done by using the sparse matrix. Obviously, like if I'm talking about India, like let us take a sample size, almost 140 is the population, 140 crore. So out of, if I'm taking only 30%, or let it be 20 crores are using Facebook, so we are getting a square matrix of dimension 20 crore by 20 crore. It's quite means impossible to create a matrix of that dimension to put it in a database. So to resolve this complexity, we can use the sparse matrix. This is one of the application, although there are many more applications. The second, we are having a full or sparse, full matrix or dense matrix. So matrix is said to be full or dense. As the name indicated, like most of the elements of this matrix are considered as a non-zero elements. Most of the elements are considered as a non-zero elements. So it is quite opposite of the sparse matrix. Like suppose that now in place of connection, we want to see how many disconnection is there. So we can do the complement of a sparse matrix and we can obtain the full matrix or dense matrix. If I'm talking about application, the first application, as I already discussed, the social media networking. So this is some data, or you can see, since it must be a square matrix first thing. It is the data representation, so it must be a square, and you can observe that most of the elements of this matrix is 0. So we can say it is the application or example of a sparse matrix. If I am talking about dense matrix application, it is used in the image processing. It is used in the numerical simulation when we are solving a large system of equations. It is also used in solving the linear system of equations. So these are some application for full matrix. Talking about sparse matrix, as already discussed one application in detail. Three more application I listed over here. It is used in the natural processing. Natural language processing means one of the example can be machine learning. Another example can be anything where we are processing a language through some of the matrix or uh, through some of the data in form of a matrix, better to say. It can used in network analysis, as the example was taken. Also used in the optimization problem, like linear programming problem is there, integer programming problem is there. We are having, beside linear and integer programming, there are like game theoretical based problem. And these matrices are also used in nature inspired algorithm. Like if any of you heard the term nature inspired algorithm, like we are having particle swarm optimization. So it is based on the activity of a swarm. In the same manner, we are having uh, uh, ant colony bee optimization, which is on the basis of the behavior of the ant in their colonies. So these are some of the applications of these two things. So this is the last topic that we left over. So now finally our syllabus for the linear algebra is completed. Nothing is left over. As I discussed earlier, now I am going to start the introduction or about the Jacobi method. As discussed with you, it is used to find the eigenvalues and eigenvector. There are certain steps that we must follow in order to process by using this method. So I am going to start this method. Those who was present, they can raise their concern, whatever not clear in the offline class here, or those who was absent, no concern, it is a fresh thing to them. Now, Jacobi method, first thing, it is an iterative method. Second thing, it is used for only symmetric matrix. It is used only for symmetric matrix. The process is start as how we are supposed to convert, a matrix into diagonal form, which is also known as the diagonalization of a matrix. So once the matrix is converted into diagonal form, we can observe the diagonal entries of the matrix is the eigenvalues, and for eigenvector we need to construct some kind of orthogonal matrix, and by using that we can also get the eigenvectors. So now the first thing is what the step number first is says that we need to choose the largest non-diagonal elements of the matrix. The first step is what we need to choose the largest element, non-diagonal, largest non-diagonal element from the given matrix, So when I'm talking about largest matrix, largest non-diagonal element, remember we are talking in terms of the magnitude. So if entries are negative, we need to take its magnitude, and whichever is having the largest magnitude, that we need to select in the step number 1. We need to select that in the step number 1. So if suppose that let Aij, I am taking a journal entry Aij, a matrix journal entry. Let Aij is the largest non-diagonal element. So once you identify a non-diagonal element, then what we need to do in that case is we need to substitute put. Now we are in the process of constructing a orthogonal matrix. Let us see how the process will begin. So what I need to do, I will put Aij as sine theta, then Aj as minus of sine theta, Aii as cos theta, and Ajj as cos theta. These are the standard selection to make a orthogonal matrix. Now, like some of the author is interchanging the sign between Aij and Aji. So you can take Aij as minus sine theta, Aji as plus sine theta. Both give the same solution. There is nothing is means no change in the final answer if you are changing this thing. Now, once you constructed this thing, like once you decided the values of Aij and Ji, then in step number 3, we need to construct a orthogonal matrix. So now the orthogonal matrix, I'm giving the name as P. So this matrix P is obtained by substituting these values. So when we are putting Aij, Abi and these things, here we need to take care one more thing. We need to put rest of diagonal elements as 1 and non-diagonal as 0. We need to put rest of diagonal elements as 1 and non-diagonal 0. And non-diagonal elements as 0. So in this manner, we will obtain the orthogonal matrix P. Now, as we are having one unknown theta here, like sine theta, cos theta. So now we need to calculate theta. Now find the value of theta, which can be obtained by equating the matrix in the diagonal form. So the value of theta, I am writing it directly. How it comes out? It will comes out as 1 upon 2 tan inverse of Aij. What is Aij? The largest non-diagonal elements divided by Aii minus Ajj. So this is how we can calculate the value of theta, which we are assuming for the elements Aij, Aji, Aii, and Ajj. So step number third is saying that we need to find the value of theta. Now, next step number 4, what it is saying? It is saying we need to find the value of that P inverse, that is your diagonal matrix inverse. A is the given matrix into P. We are finding the value of P inverse A into P. So it is also comes in terms of a matrix. Now, if this P inverse AP comes as diagonal matrix, our task is done. If this P inverse AP comes as a diagonal matrix, our task is done. And the elements which are on the diagonals are the eigenvalue of the given matrix. Is the eigenvalue of the given matrix, and corresponding eigenvector are the column of your diagonal matrix P. Orthogonal matrix P, not diagonal. So your task is done. So I am writing it. If diagonal matrix obtained, if diagonal matrix obtained, then the diagonal elements, will be the eigenvalues of matrix A. If this comes out as diagonal matrix, the task is done. Our diagonal elements are the eigenvalues of the given matrix A. But what happens if this matrix is a non-diagonal element? Non-diagonal form, better to say. What we mean by non-diagonal form? That except the diagonal elements, there are some more elements which are non-zero. This non-diagonal element, if all the non-diagonal elements are zero, we call it as a diagonal matrix. If it is not, a non-diagonal matrix. So now the next thing is that step number 6, if this P inverse AP is a non-diagonal matrix, Here what I mean by non-diagonal means except there are some more elements which are non-diagonal and non-zero. So if this happens, then what I will do, I will repeat the earlier process once again. If this happens, then the earlier process will be repeat once again. Or we can say, then we will proceed for second iteration for second iteration by taking this P inverse AP as a matrix, as a given matrix, as a given matrix. So if this is non-diagonal, whatever P inverse AP comes out, that will be our new given matrix. It's not like whatever original is given, that is used in the first step. In the second step, the matrix is used. Which matrix is used? Which is comes as P inverse A into P. Now we'll repeat the same procedure over here. We will select the non-diagonal elements, the largest non-diagonal elements. Once again, we are supposed to find the value of theta. Once again, we need to find the diagonal matrix. Let us this time we can take it as P1. Once again, we need to find the value of P1 inverse A into P1. And if it is comes out as a diagonal matrix, the task is done. The diagonal elements are the eigenvalues of the matrix. If this is not the case, we will repeat the same iteration, step number 6. So these are 5 to 6 steps that we are having for finding the eigenvalues for a given matrix by using the Jacobi method. So let us revise it once again, what I am just discussing till now. The first step is what? This method is used only for the symmetric matrix. So do make a note for it. If a matrix is non-symmetric, this method can't be used. It is only used when either we can convert the matrix into symmetric or directly the matrix is given in the symmetric form. The first structure is what? We need to construct a orthogonal matrix, which can be obtained by selecting the largest non-diagonal element from the given matrix. We are generally giving the name as Aij, and this is what the substitution we will do for making the diagonal matrix. Do take care one more thing, except these entries, the rest of the diagonal elements are considered as 1 and non-diagonal elements are considered as 0. Except these 4 substitution, the rest of the elements is what? Either 1 or 0 for diagonal 1, for non-diagonal 0. So now we will construct that orthogonal matrix P. Over here, the theta will be calculated like this, and then we'll proceed for finding P inverse AP. Since I am saying the matrix is orthogonal, so since P is orthogonal, so we know a result for orthogonal matrix. If P is orthogonal, then P into P transpose gives you identity. P into P transpose is identity, then the matrix P is orthogonal. Here, from here, we can take one more thing. We can like divide the whole equation by or multiply the whole equation by P inverse. So P inverse comes out as P transpose. So it's not like we need to use some separate methods for finding the P inverse. It can be directly obtained. Whatever your P orthogonal matrix is there, do its transpose, and that transpose will be the inverse of the matrix. So now your P is obtained, P inverse is obtained, and A is the given matrix. So using the 3 things, you need to find P inverse A into P. Normal simple matrix multiplication. And if this multiplication gives you a diagonal matrix, then our task is done. The diagonal entries are the eigenvalues of the given matrix. If this is not the case, then we will proceed to the iteration number 2. What iteration number 2 is saying, whatever your P inverse AP is obtained, that is in this multiplication, we will consider it as a given matrix and once again proceed for the same process that we are discussing. Like select the largest non-diagonal element. Then on that basis, we need to find inverse, and once again on that basis, we will find P1 inverse into A into P1. Whatever comes out, once again we need to check it whether it is a diagonal matrix or not. Once the diagonal matrix is obtained, the task is done. If not, will repeat the same process. So the process or this Jacobi method is based on the concept to reduce the given matrix into a diagonal form. To reduce the given matrix into a diagonal form. So this is what the working rule that we are having for Jacobi method. Now I am going to take an example so that the process will be more clear to all of you. If there is any doubt or any concern in the process, you can ask for it. So I am taking the example. The question is what? Find the eigenvalues. Find the eigenvalues and eigenvectors for the matrix A equals to, I am taking a random matrix. Do remember the matrix must be symmetric matrix. So 1, root 2, 2. So this is root 2, so it must be root 2. Diagonal may be anything. So this is also root 2 I am taking. This is 2, this is root 2, and this is 1. You can observe the matrix is a symmetric matrix. So we need to find the eigenvalue, eigenvector for this matrix by Jacobi method. Jacobi method means we need to find the eigenvalue, eigenvector by using the iterative method. So now let us start for solution. So as I already discussed with you, what is the first step? The first step is what? We need to find the largest non-diagonal elements for the given matrix. Now it can be easily seen that the largest non-diagonal element for the matrix is 1. So what is non-diagonal? These elements are the diagonal elements. So non-diagonal we are having root 2 and 2. Out of root 2 and 2 is the largest element. So the first thing is what? We need to select the largest element, which is selected. So this is the non-diagonal largest element. What is the name of this one? A13. A13, first row, third column. So A13 is 2. A13, what I'm getting, A13 comes out as 2. So what will be A31? A31, also you can see it's 2. What will be A11? It is 1. What is A33? It is also 1. Why I'm writing A11, A33? Because they are needed when we are supposed to calculate the angle theta. Just see the formula for theta. A1ij, Aii, Ajj. So this is what we need to use when finding the value of theta, not for the orthogonal matrix. Okay, so this is what the largest non-diagonal element that we are getting. So now what the next step? We need to make a orthogonal matrix and then we are supposed to find the value of theta. You can do it in any process. Either you can first find the value of theta, then you can write orthogonal matrix, or you can first write orthogonal matrix, then you can proceed for finding the theta. So now I am going to find the matrix P, the orthogonal matrix P. So for that, what I need to do? So remember the substitution. We need to put what I need to put. A13 I must put as sine theta. A31 minus of sine theta. You can interchange these two also. Now A13 sine theta, A31 cos theta, A11 as cos theta, and A33 is also cos theta. From where A11, A33 comes? Because it is A13, the largest one. So put it in the matrix. So this is your sine theta because it is A13. So this is your sine theta and this is your minus sine theta because A31. Now A11.
So A11 is cos theta.
Correct, correction. Because A11 is there. So firstly, A11 is cos theta. So this is your A11. 33 is also cos theta. So this is your cos theta. Now A13. So first row, third column, this is your sine theta. And this is your minus sine theta. Now, what diagonal entry left? The center one. So this is one. Non-diagonal, put them 0. So this is what the orthogonal matrix that we are obtained over here. Cos theta 0, sin theta 0, 1, 0, minus sin theta 0, cos theta. Now I am making it as equation number 1. Now what the next thing I need to see? I need to find the value of theta. So we have how to calculate theta. Theta is equals to 1 upon 2 times tan inverse of Aij upon Aii minus Ajj. What is Aii? Aii is the largest non-diagonal elements. So if I'm writing in terms of the given, your Aij is what? A13. So this will be A11 minus A13. So put those value over here, which is equals to 1 upon 2 times tan inverse of A13. So the largest is 2, 1 is 1 and 1 3. This should be 3 3. So what I'm getting, this gives me infinite. So tan inverse infinite, theta is equals to, correct, theta equals to 1 upon 2 tan inverse of infinite. So pi by 2 into 1 upon 2, pi by 4. So we have done two things. First, we find the orthogonal matrix P and then we find the value of theta. Why theta is needed? Because it is used in the orthogonal matrix P here. Now I am going to put theta in your P, that is the orthogonal matrix. So put theta in P. So now we are supposed to put this theta in your orthogonal matrix P. Now put theta in first, since I make it as a first. So P is equals to, the first one is cos theta. Let me check it. What is it? Yeah, cos
1 by
theta.
root 2.
So cos theta is 1 by root 2. Then sin theta is also 1 by root 2. So let us put the values in terms of angle that I have obtained. So what it comes out? So 1 upon root 2. So this will be 1 upon root 2. This will be 0. Sine
0.
pi by 4 is also 1
1 by
upon
root
root
2.
2. 0, 1,
1,
0,
0.
minus 1
Minus 1
upon
by
root
root 2.
2, 0, and then 1
1 by
upon
root.
root. Correct. So this will be our orthogonal matrix that we are searching. Now we need to find P inverse. So P inverse will be what? As the given matrix or P is orthogonal. So P inverse is same as P transpose. And what we mean by transpose of a matrix? Interchange row and column. So this will be looks like 1 upon 2 root 2, 0, 1 upon root 2, 0, 1, 0, minus 1 upon root 2, then 0, and then 1 upon root 2. So three things done till now. First, we constructed the orthogonal matrix P in terms of theta. Second thing, find out the value of theta by using the process. And then we find the value of P inverse, which is same as P transpose. So now what the next thing? The last step in the iteration number 1, we need to find. So next step is saying we need to find the value of this P inverse into A into P.
बघा ना सर, म्हणजे किती तुम्ही थोडा सुद्धा मुलांचा विचार करत नाही का सर?
This is what P inverse A into P I
हा ना,
need to find.
किती वेळा त्यांना सांगितलं तरी ते नाही ऐकत.
Sujata Jadhav, please. If you are busy somewhere else, please off your mic. So now we need to find P inverse A into P. So P inverse that we are having is 1 upon root 2, 0, and then minus 1 upon root 2. Now this is 0, this is 1, this is 0. 1 upon root 2, this is 0, and this is also 1 upon root 2. This is your P inverse. Now at the center, what should I put? The value of the given matrix A. So our A, it is 1, then root 2, then 2, then root 2, then 3, and then this is also root 2, 2, root 2, and 1 into P, that is the orthogonal matrix that we have constructed. So orthogonal matrix P comes out as 1 upon root 2, 0, then 1 upon root 2, 0, 1, 0, minus 1 upon root 2, then this is 0 and this is 1 upon root 2. So this is what I need to do multiplication. So it can be in any order, either first and second multiplication with third, or second and third with first. So we can do the multiplication. I'm writing it directly how much it comes out. So 1, 0, 0, 0, 3, 2, and this is also 0, this is 2, and this is now we are getting it as 3. So this is how the first iteration is completed. We are on the last stage of first iteration, which is P inverse AP, and comes out this thing. So should I stop the process or should I move to next iteration? So as a result, we have discussed if non-diagonal elements are 0, then we will stop the process. But here you can see the non-diagonal elements are non-zero, means some of the elements are non-zero. It means the process is not stopped. We need to proceed for the iteration number 2. We need to proceed for iteration number 2, and for that, what is your original matrix? This matrix, which is -1, 0, 1, or whatever it comes, will be our original matrix. So now we'll proceed for the second iteration. So in second iteration, why I am proceeding on second iteration? It must be clear, because the diagonal matrix is not obtained. Since P inverse A into P is not a diagonal matrix, is not a diagonal matrix. So we will proceed. So we will proceed to second iteration by taking this P inverse A into P as given matrix. Is the matrix which is given originally, now shifted to 1, 0, 2, 1, 0, 0, 0, 3, 2, and 0, 2, 3. So second iteration, I am assuming here, so let the matrix I am giving the name as A1, and A1 is -1, 0, 0, 0, 3, 2, 0, 2, and 3. So now assume this is your question. We need to do the all calculation that we have done in the first iteration once again by taking this as a given matrix. So second iteration now will start it. So once again we need to select the non-diagonal largest element, which is once again 2. So let, or better to write here, the largest non-diagonal element here, the largest non-diagonal element is what? A23 is A23, which is 2. Largest non-diagonal is obtained. Also, A23 is 2, so which is same as A32. So now what I need to take A22, because 23 is there, so one is A22 and one is A33. So A22 is 3 in the problem and A33 is also 3. Why I needed these 4 values? For finding theta. So now I am starting to find theta first.
Sir, it should be 832, no? Or 823. One and the same. Okay.
Okay, so now we are proceeding to find theta. So 1 upon 2 tan inverse of 1 upon 2 tan inverse of 2 of aij, 2 of aij. So largest element is a23. It doesn't matter whether I am taking 2, 3 or 3, 2 because both are same.
Yes, sir. Yes, sir.
So divided by a22 minus a33. So I need to put the values. It will comes out as 1 upon 2 times tan inverse of a23 is 2. So 4 upon 3 minus 3 once again comes out to be 0. So once again pi by 4 as in the first step. And do make a note, we will taking theta from minus pi by 4 to plus pi by 4 only. Yeah? So the theta is obtained from here pi by 4. Now the next diagonal matrix I am making it as P1. So what will be your P1 if I am putting the values? So A23. So I am taking 1. So these
Sir,
are the
formula for tan inverse, can you repeat? Is it Aij upon Ai minus Aj? Why
It's
we
a-
have taken twice in this?
no, that is twice only.
Yeah.
Earlier what I did twice or normal?
No, sir.
No, sir, we have
That's
not
what.
taken.
Okay. So this is one. So make it correction. It is in original formula. It is twice exactly. So do correction. It is in original formula. It's twice. So let me write it over here. If we need, we can go through with the proof also why this 2 is there. No problem for that. So this is small correction, done, correct. Since the denominator is 0, so that's why it's not affecting whether it is 2 or only 1. But in a standard formula, it's 2 in the numerator. Okay. So now putting the value. So now the new P1 will be what? This is 1, this is 0, this is 0, this is 0. So this is what? A22. So what we are putting for A22? So this is our substitution. If I do write it, what I need to put. So for orthogonal matrix, I need to put A23 as sine theta, A32 as minus of sine theta, and then once again A22 as cos theta and A33 as cos theta. Substitution for orthogonal matrix. So center is A22, so it is cos theta, and this will be 0 because this is cos theta, and this is A23, so sine theta. This will be 0. This will be A32, so minus of sine theta, and this will be cos theta. So this will be new orthogonal matrix. I am making it as P1. Now we need to put theta as pi by 4. So if I put theta as pi by 4, this will be 1, 0, 0, 0, cos pi by 4, obviously 1 by root 2. This is also 1 by root 2, 0, minus 1 by root 2, and this is also 1 by root 2. So P1 is obtained. Also, I need P1 inverse, which is P1 inverse is nothing but P1 transpose by using the property of orthogonal matrix. So this will be looks like 1, 0, 0, and then 0, 1 by root 2 and 1 by root 2, and this will be 0, minus 1 by root 2 and 1 by root 2. So we have obtained P1 inverse. So now the last step of second iteration. Now we are supposed to find what? We need to find P1 inverse into new matrix is A1 into P1. As earlier in the first iteration, it is P inverse A into P. But since in that iteration we didn't obtain the diagonal matrix, that's why we need to proceed over here. So P1 inverse, which is 1, 0, 0, 0, 1 by root 2, minus 1 by root 2, 0, 1 by root 2 and 1 by root 2. This is your P1 inverse and new A1. What is new A1? It is minus 1, 0, 0, 0, 3, 2, 0, 2, 3. This is your A1 and now P1 inverse. I suppose to put it over here. So which comes out as 1, 0, 0. Now 0, 1 by root 2 minus 1 by root 2, 0, 1 by root 2 and 1 by root 2. So we have put it all the values over here, which is P1 inverse, A1, and then P1, the orthogonal matrix. Now by usual matrix multiplication, we can do it. So if I do the multiplication, I'm directly writing because I'm having it. So this comes out as minus 1, 0, 0, 0, 1, 0, and last is 0, 0, 5. So now we can observe the resultant matrix comes out as a diagonal matrix. Non-diagonals are 0. So now we will stop the process, or we can say the process is terminated. No need to proceed for the iteration number 3. So we will conclude here, which is a diagonal matrix, which is a diagonal matrix. Diagonal matrix. So the process will stop. So the process will terminated, or we can say stop, and the diagonal elements of P1 inverse, A1 and P1 are the eigenvalues of the given matrix A. Given matrix A. Do remember, for the given matrix A, it's not like what the matrix is converted. Hence, the eigenvalues are, the eigenvalues of A is, it's minus 1, 1 and 5. Minus 1, 1 and 5. So the eigenvalue of the matrix is obtained by using the Jacobi method, which is minus 1, 1 and 5. So this is what the method is known as the Jacobi method, and this is how we can proceed. If having any concern, you can ask for it. Still the process is not, question is not completed, because the question is asking both the things, eigenvalues and eigenvector. What we find just now, the eigenvalues only. Now how to find eigenvector, that is also a simple step. Now for eigenvectors, now for eigenvector, what we need to do, whatever orthogonal matrix we have obtained, their multiplication will gives you the set of eigenvectors. So here we are having two orthogonal matrix. One is P1, another is P. If suppose that third iteration is there, then P2 is also there. Fourth iteration, P4 is also there in the same manner. So whatever we are getting the orthogonal matrix, their multiplication, that is P1 into P. So what P1 I am having in this question? So P1 is what? 1, 0, 0, then 0. This is 1 by root 2. This is also 1 by root 2. This is 0. This is minus 1 by root 2, and this is 1 by root 2. This is your P1. And then we need to write the matrix P. What P we have obtained? Yeah, so this is P. So 1 upon root 2. then it is 0, then it is 1 upon root 2, 0, 1, then 0, minus 1 upon root 2, then 0, then 1 over root 2. So this is what we are getting as P1 and P. So we need to do their multiplication. So do the multiplication and whatever comes out, that will be our set of eigenvectors. So it will comes out as I am writing directly the multiplication 1 upon 2 minus 1 upon root 2, then minus 1 upon root 2. This will be 1 over root 2. This is 1 over root 2. This is 0. So this is 1 upon 2. This is minus 1 upon root 2. And this is also 1 over root 2. So this is the matrix that I have obtained after multiplication of the orthogonal matrices that are used in iteration 1 and iteration 2. Since we are having 3 eigenvalues, so these are the 3 eigenvectors. So eigenvalue corresponding to eigenvector corresponding to first eigenvalue. This is first eigenvector. This is second eigenvector, and this is the third eigenvector. Do remember one thing, in whatever order the element is there on diagonal, the same order will be followed over here for writing the eigenvector. For example, the first diagonal element is -1. So the first eigenvector, which is this row, is for eigenvalue -1. So order must be followed. So what I should write, this is what eigenvector for eigenvalue -1. This is the eigenvector for eigenvalue -1. The second diagonal element, if I see it again, it is 1. So the second one, this second is the eigenvector for eigenvalue, which is 1. And the third is the eigenvector. This is the eigenvector for eigenvalue, which is what? The third eigenvalue, it's a 5. So this is how we can use the Jacobi method or Jacobi iterative method to find the eigenvalues and eigenvector for a given matrix. See the whole process once again. If there is any difficulty or doubt from your side, you can ask for it. Obviously, the method is quite lengthy. If suppose that we get diagonal matrix in the first iteration, then it's done. But generally, it's not happen. At least 2 iteration is there, or sometime more than 2 is also needed. Ultimately, we will stop only when we get a diagonal matrix. The diagonal matrix, we will stop the process. Otherwise, we will continue the same. At last step for eigenvector, whatever orthogonal matrix we are constructing in each iteration, their conjugative multiplication gives the eigenvector. Do remember this thing also, like top left orthogonal matrix is from the last iteration. Then next one, second last. Then next one, third last. And the top right orthogonal is from the iteration number 1. So we need to follow this order also because matrix multiplication is not commutative. Understood? So this is how we can find the eigenvalues and eigenvector. See it again, the whole process. If any doubt is there, you can ask for it. Just go through with the whole process for the next 5 minutes. If you feel there is something from your side, you can ask for it. Okay, so if nothing is there from your side, this is the last topic or the last thing from the linear algebra syllabus. So your syllabus is now finally completed. Although meanwhile, if you are having any concern or doubt from any topic from linear algebra, you can write to me on the email, or if you are present in campus, you can come to meet in my cabin. It's on the first floor. So if nothing is there, let us close the session.
So kindly share this material with us.
No problem. I will share it in the Google Classroom, the same file that we are just discussing, the same file, the handwritten file.
Yes.
Any other point from anyone else?
I mean the offline class. If I have any doubt, I will mail you. Sir.
No problem, no problem.
Sir, also the yesterday recorded session you will post on the classroom now.
No
Today's-
problem, no problem. I will post it.
Thank you.
Yes, sir. How will be the marks distribution for all the subjects, like whatever
Actually-
comes under?
Actually, in end semester exam, the weightage for this linear algebra part is 20 marks. Okay, in 20 marks, probably you will get 3-4 questions, 5 marks each. And the highlight that we have discussed in linear algebra is what? Surely one questions on stochastic or random process, stochastic, random, and Markov. One question from there. It may ask for the transition diagram or transition probability matrix. One question from system of linear equation that we have done solution. Like if I remember, we have solved the inconsistent system of equation by a method of least square. And I think another method is somewhat Jacobi method is there also. So out of those two, surely one question. And for eigenvalue, eigenvector, as I remember, we also discussed two methods. One is Jacobi method. One more method is there. I didn't remember the name. I think power method. Yes, the power method, which is used to find the largest or smallest eigenvalue from a given matrix. So either power method or this Jacobi method. Surely one question will be there. So it will be 1, 2, 3. We have also discussed, I think, Gauss-Seidel and Gauss elimination method, which is used to find the approximate solution. So from there, one question. So quite limited topic, 8 to 10 topics are there. And probably from each and everything, we will get single question. If
Okay.
weightage is 5 marks out of 20, so 4 question at least.
Okay, sir. Thank you.
Anything else? Okay, if nothing is from your side, let us close the session.